Differential Equations, Section 3, Numerical Solutions. Video 5, the Runge-Kutta method, Order 4. The Runge-Kutta method of approximating numerical solutions to differential equations was developed around 1900 by the German mathematicians Carl Runge and Wilhelm Kutta. Now, the modified Euler method that we've already seen is based on using a weighted average of the derivative across each step. This idea of averaging is known as a Runge-Kutta method, but when people say the Runge-Kutta method, what they usually mean is the Order 4 method. So the modified Euler method in the previous video used two approximations, K1 and K2, to the change in y, and then averaged them out in order to find our new value. This time we've also got K3 and K4. And then we find a weighted average of all four of those to get our new y value. Let's go through the k values one at a time then. Well, first of all, we've got h times f of xn and yn. This is just the very first approximation that we used when we first introduced the Euler method. My second k value then, k2, is h times f of xn plus h over 2 and yn plus k1 over 2. So this h over 2 just here is because we're thinking about the middle of the interval that we're stepping over. So we're taking a step size of h, and so h over 2 is halfway along. So this is an estimate based on what the gradient will be halfway along the distance. And the y value here is k1 over 2. For K3, I'm also looking at a step halfway along the distance, but this time I'm using the K2 value that I've just found and putting that in to get my estimate for the gradient. And then my final estimate for the gradient is based on the full interval, so xn plus h and yn plus K3, the value that I worked out at the third step here. And then all of these are put together. So my new y value is my original value yn plus a sixth of k1 plus twice k2 plus twice k3 plus k4. Now, I've taken the leftmost approximation, the rightmost approximation, and then twice each of the middle two. And I've divided by 6 because it's a weighted average. I've added up 6 k values altogether. 1, 2, 3, 4, 5, 6 of them. So where does all of this come from? Well, you don't need to know a formal derivation of this method, but it is nice to have some background. So if you're doing the numerical methods option, you might have already met Simpson's rule for numerical integration, and the Runge-Kutta method Order 4 can actually be derived in a very similar way. So Simpson's rule is for integration, and in the same way that the trapezium rule uses straight lines to approximate an integral, Simpson's rule goes one step further and uses curves, specifically parabolas, for each step. And here's the formula for Simpson's rule. The integral from x0 to x1 of f of x dx is approximately h over 3 times y0 plus 4y1 plus y2. And so this one of these, 4 of these, and 1 of these is very, very similar to what we had with our k values. The only difference is that we had k1, 2k2, 2k3, and k4. y0 and y2 are the two endpoints, and y1 is the midpoint. My k2 values are just two different ways of doing that middle, so that's why it's split up into 2 and 2 rather than one of them being 4. And the other difference between Simpson's rule and the Runge-Kutta method is that we've got h over 3 here. That's because the way that the intervals are defined is slightly different, so we've divided things up into 6, whereas Simpson's rule is dividing things up into 3. So now that we've seen the background to the Runge-Kutta method, in the next video we're going to see an example of how to apply it. In this video you've learned the definition of the Runge-Kutta Order 4 method, and you've seen how Runge-Kutta Order 4 relates to Simpson's rule.